where 1 unit is, so it's written in sexagesimal.
Right.
But it's, you have to be careful to read how to interpret this, right? Because it said, it's a sexagesimal number, but actually, the first digit is parts per 120. So it's like half. So you get the sexagesimal number. You see that I've got the C2 cell divided by 60. That was the minutes divided by 60. And then the D2 cell divided by 60 squared. Then that sum, I take half of. Why? Because it's parts of 120 instead of parts of 60. And why parts of 120? It's trying to be more accurate, right? So getting down to a finer mesh.
So for that column, do we put it in decimal form, or are we supposed to leave it in the minutes and seconds?
Well, you're supposed to have, yeah, this should be just one column, these 2 columns.
Yeah.
Yeah, that's just reading the poetry from Sanskrit, right? And interpreting that as this many minutes and that many seconds, even though,
Yeah, because
parts
it
per
says for
one.
the third column, to like divide it in half, so I just half of the minutes and seconds.
Oh,
Grab a snack.
oh, yeah.
He
no,
moves
I-
around.
interpret that
I'm not
as
too
one.
worried about it. Just if he's over here, I'll be back.
So, should I reread that? So maybe I can sweat it. So, where are we? So, part 2E. I guess, so we have to reread. Yeah, so, finally, in verses 6 through 8, Vareh HaMehira begins the recitation of the entries of this table of sign values. He fixes the radius of the circle as 120, or 2 units of 60 minutes each. This will become clear, okay?
I think it's in D.
In D, we
Yeah,
say,
so it's
check that
to
the value,
determine the sign.
yeah, okay. Vareh HaMehira's table are correct as follows. His sign values correspond to a line segments drawn relative to the radius of 2 units equals 120 minutes. So modern sign values, lowercase s, corresponding choosing a radius of r equals 1 unit. So add a third column to your table and place here the signs of these same arcs. To determine the signs, convert the sexagesimal sign values into minutes, seconds, which appear in the second column, into 2 sign values in minutes, seconds, by cutting them in half so that they correspond to a circle with a radius of 1 unit radius. Yeah.
I left it in minutes and seconds, not like decimal.
So what did you write? First, let's look at the first one. Say. So I have here, oops, so did you write like 3?
Yeah, I did 3.5 and 25.5, but then I yeah, I left it like that.
Well, I think the whole point of this, at least the way I understood it, was that you actually can get a decimal value for these and then compare that with the calculator value of, so this is a decimal value for the sign according to these data that are given in the ancient text. And these are what a modern calculator would compute for these angles. And they're very close, right? That's the whole idea, is to see how close they are. Yeah, I agree, it's a little confusing there. So let me go back and reread. What is exactly, I mean, if you're doing what he tells you to do, I can't argue with that, right? Check that the values at the table are correct. I mean, how would you know whether that's correct or not? Yeah, I mean, if you just take 3.5 minutes and 25.5 seconds, is that correct?
But
Who's
would
to know
I still
whether-
have to divide by the 60?
Yeah.
And, And if it's the same thing, then I would just leave it like that?
Yeah, yeah, I think you wanna convert those, it doesn't say so much, does it?
It just says by cutting them in half, so they correspond to a circle with 1 unit radius.
So to convert the sexagesimal sign values into minute seconds, which appear in the second column into sign values in minute seconds, by cutting them in half so that they correspond to a circle with, finally, let's prepare a decimal version. So let's relook at part E then. So, you know, if you had that as your third column, you're kind of following the instructions, which I can't argue with. But then if you look at E, prepare decimal versions which we can use to check his values against the gross computer in a calculator. Begin a new table by translating the 6 arcs angles from degree minutes into decimal degrees. So I just kind of, actually, I just kind of skipped D, didn't I? And I didn't prepare a new table. I just put it in the same table. So I guess I reinterpreted the question a little bit. So I completely appreciate your pointing that out. But you do need, for part E, to convert those 3.5, 25.5 values into
Decimal.
decimal, and then compare with the calculator. So quite a good point you make. All right. So where are we then? We're down here to the direct shadow and the, yeah. So so we have this picture, right, where it's a new interpretation of the geometry. This is somewhat different. So here's, if you have a gnomon, which is a stick stuck in the ground, right, it's going to cast a shadow. And the sun is at point A there, shining down at an angle from the stick. And it, you know, it really doesn't matter where you put this thing. Why not?
Doesn't change the angle.
Yeah, why not? Because the sun is so far away, is the answer to that, right? So, if you were closer to the sun, then, you know, if you shift a little bit, then, you know, you shifting the angle. But the sun is so far away that all the rays, sunlight rays coming in from the sun to the earth are virtually parallel, right? So slightly not parallel, but it's such a slight difference that it doesn't really, it'd be impossible to measure easily. So you can think of all those things coming in. So no matter where you put this, you're in a stream of parallel rays coming in, and you're going to end up with the same picture. The gnomon BG casts a shadow GE, depending upon the length of the gnomon and the arc of angle of the sun, of the elevation of the sun, right? So, yeah, so then you also have this reverse thing. If you were to, say, put a stick in the wall perpendicular to a perpendicular, so the wall is perpendicular to the ground, and the stick is perpendicular to the wall, the sun is going to shine on this and make a shadow here, right? So you get one shadow from a vertical stick and another shadow from a horizontal stick, and those correspond to complementary arcs of elevation. So when you turn it sideways, you get the complement. And so task 23 is to copy the 2 diagrams provided with the text, then label these elements, the sun, the circle of altitude, the altitude of the sun. Did we do this last time? I seem to recall them doing that.
Yeah.
Yeah. So then we have this picture.
So I have a question, a quick
Yeah,
question
go
on this
ahead.
topic. How this relates to like sundials? Did they ever need to be calibrated at all, or did they just always work because the sun was just off above you at noontime?
Yeah. So the same sundial.
Because I think I remember them looking like at a triangle, like a table with a triangle, like a dolphin fin, kind of sticking up at a particular angle. If I ever seen one.
to know how to read a sundial, you have to kind of figure out what altitude you're at. And you can do that by taking a reading on a certain day of the year, right? Like the winter solstice
Oh,
or
I see.
the summer solstice in particular.
Why would the altitude affect it? Because isn't the sun so far away, it wouldn't change the angle very much either, like you said before?
It's because of the tilt of the Earth. So yeah. So as the sun, as the Earth progresses throughout the year around the sun, it shows a different inclination towards, your particular altitude will have a different angle of inclination towards the sun because of the tilt of the Earth. If the Earth weren't tilted, then yes, what you say is true, that it wouldn't matter where you are, you wouldn't be able to tell your altitude from the angle.
So everyone would have to get like a reading or something from whoever they bought it
Or you
from
wouldn't be
before.
able to tell the time of the year. You could tell your altitude, but you couldn't tell the time of the year. So it's because of the tilt of the Earth that the sundial allows you to tell what day of the year it is, given your altitude, and allows you to compute your altitude as well.